Chapter 14, Part 2, we are going to continue talking about probability, and in this video we will talk about some of the basic probability problems. So the first thing that we need to talk about is some notation for probability. We've learned that when we're talking about just the probability of one event, maybe that event is A, that we would call it probability of A. There's two more very common options. We could find the probability of A and B, or we could find the probability of A or B, where A and B are two different events. So maybe A is rolling a dice and B is picking a card from a deck of cards. When we're finding the probability of A and B, we will use this notation here. We'll still start with our capital P representing probability. In parentheses, I'm going to put A, and then and is a U but upside down, B. So this is read probability of A and B. For probability of A or B, we would still start with our capital P for probability. For or, you use an upside or a regular U. So this is A or B. Okay, we are dealing with probabilities now, not data, so we're kind of switching gears a little bit here, but the three main rules don't change. You want to make a picture. Having a picture of what's happening can be very, very helpful here. Since we are working with probabilities now instead of data, our pictures are going to change. For data, we used histograms and box plots and dot plots. Now for probabilities, we're going to have a few different pictures. The most common type of picture to make is a Venn diagram, which I know you guys have all seen Venn diagrams. You typically use them in like history or English, something like that. Maybe you've seen a Venn diagram for math in your geometry class. What our Venn diagrams will look like is we'll actually start with a box. Venn diagrams typically will have two circles. They can overlap, they don't have to overlap. Each of these circles would be representing an event. So I'm going to label one circle event A and the other circle event B. Now for this example, I'm going to have A represent odd numbers, and we'll only go 1 through 10. B is going to represent numbers that are greater than 5. We'll do greater than or equal to 5, and also less than or equal to 10. So we're only working with numbers 1 through 10. A are all my odd numbers, B are numbers 5 through 10. So if I'm going through my numbers here, just 1 through 10, 1 is an odd number, so that can go in A. It's not going to go in this overlap because it's not greater than 5. 2 is not an odd number. It's also not greater than 5, so it would go on the outside. It does not fit into either of my events. 3 is an odd number, so it would go in just A. 5 is my next number. That is an odd number, so it's part of event A, but it also is part of event B, so it would go in this overlap. 6 is not odd, but it's greater than 5, so it would be B. 7, again, is in the middle here. It's in both. 8 is in just B. 9 is odd and greater than 5. And then 10 would just be here in B. We will use a lot of these Venn diagrams in the next couple sections of our probability notes. The next few sections here we'll talk about formal probabilities. So these are kind of some notations or facts about probability that we'll need to know and need to use quite frequently. So the first thing is there are two requirements for probability. The first is that a probability is a number between 0 and 1. So in our notation here, for any event A, we would say that the probability of A is greater than or equal to 0, less than or equal to 1. The smallest probability you can have is 0. The largest probability you can have is 1. Probabilities are percentages. I can't have something be a -% or 110%. The second formal probability that we'll talk about is called the probability assignment rule. This says the probability of a set of all possible outcomes of a trial must be 1. So if we are using S to represent the set of all our possible outcomes, you could also think of this as your sample, then the probability of this sample in total should always be equal to 1. Okay, sometimes people, as a picture, will draw their box here, kind of like we did with that Venn diagram. Anything in this box is considered your sample. The probability of this sample is always equal to 1. Everything in there always should be equal to 100%. Okay, the next we have the complement rule. This says that the set of outcomes that are not in event A are called the complement of A. And there's a few ways that we can denote this. You could note this as A with a little c. That means the complement of A. Or you could write it as A with just a little kind of dash. Both of those are representing complement of A. So these are things that are not in the event A. Okay, so the probability of event occurring is 1 minus the probability that it does not occur. So, for example, using our notation, if I'm trying to find the probability of A, I could take 1, that's again coming from this idea that our entire sample has to add up to 1, and I could subtract the probability of that event not occurring. Picture-wise, I'm starting with my big box here for my sample. If event A is just this little piece over here, then to find what's left over, to find our complement of A, I would just take 1, because this whole box has to add up to 1, so just take 1, subtract the probability of A occurring, and I'd be left with what's left over. We use this idea of complements all the time. We may not realize that we're using probabilities, but we do use it. For example, suppose there is a 35% chance that on your drive to school, a particular stoplight is green. So 35% chance that this light's going to be green. We want to find the probability that the light is not green. Okay, so I'm going to use notations here. I am trying to find the probability or the chances that it's not green. So using my notation, I'm going to write this as probability of green with my little dash, or green prime. That's not green. Okay, well technically what I'm going to do here is take 100%, and I'm going to subtract the chances that it is green. Well, they told me there was a 35% chance that it is green. 1 minus the 0.35 would give me 0.65. You can leave your answer just like that, or you could change it to 65%. Either one of these would be fine. But if there's a 35% chance that the light is green, then I know there's a 65% chance that it's not green. This idea of complements is quite a common occurrence in our daily lives. The next rule that we'll talk about is called the addition rule. So the addition rule, we'll first have to talk about disjoint. So events that have no outcomes in common and thus they cannot occur together are called disjoint or mutually exclusive. Again, I like to think about this as my picture. So if I started with my sample here, two events that are disjoint would have no overlap. So this could be event A and event B. There's no overlap. They have nothing in common, cannot occur at the same time. So if you have these two disjoint events, the probability that one or the other occurs, so the probability of A or B, is the sum of the probabilities of the two events. So using our notation here, I would say that the probability of A or B, I'm using that U there to represent or, would be equal to the chances of A happening, so the probability of A, plus the probability of B. So if there is a 40% chance that A occurs and a 10% chance that B occurs, there is a 50% chance that A or B will happen because the sum would be 0.5. Okay, so another example here using those stoplights again. Suppose there is a 35% chance that on your drive to school the stoplight is green, 4% chance that the light is yellow. Okay, we want to find the probability that the light is green or yellow. So using my notation, I'm going to use G for green, I'm using my U for or, and Y is for yellow. Looks kind of weird. It looks like the probability of a guy, but it looks like we should be finding the probability of green or yellow. To do this, I'm going to take the probability of the green light, add it to the probability of the yellow light. So the green light was the 35% chance, so 0.35. Yellow was 4%, so that's 0.04. In total, we have 0.39 or 39%. Now I'm able to just add these two probabilities together like that because these two events are disjoint. There's no way that when I pull up to the stoplight, it's going to be both green and yellow at the same time. They are disjoint, mutually exclusive. They cannot happen at the same time. The next question says, what's the probability that the light is red? Okay, I know that if it's not green, if it's not yellow, my only other option is that it's red. So to find the probability of this red light, what I would do is take 1 and subtract the probability that it's not red. If it's not red, it's green or yellow, which we just found is 0.39. So I would do 1 minus my 0.39, and I would get 0.61. Notice here that this probability of red plus the green plus the yellow should add up to 100% or just add up to 1. That's because those are the three options in your sample space. The fifth rule that we'll talk about today is the multiplication rule. This says that for two independent events, A and B, remember that independent means that these two events do not impact one another. So whatever happened at event A does not change the chances or the probabilities of event B occurring. So if A and B are independent, then the probability that both A and B occur is the product of the probabilities of the two events. So notation-wise, I would be taking the probability of A and B, so I'm using that upside down U this time. For AND problems, we multiply. So we'll take the probability of A and multiply it with the probability of B. Okay, two independent events, A and B, are not disjoint provided that the two events have probabilities greater than 0. So if I draw my little picture here again, I'm looking at my sample. If I have A and B and they are overlapping, so let's say this is A and this is B, the probability of A and B would be this shaded area over here, this overlap. If there is an overlap there, those probabilities will be greater than 0. It's a great way to show you that they are not disjoint. Okay, many mathematicians and many stats methods require an independence assumption. Meaning that we're going to just assume that the two events are independent. We don't really want to do that because assuming independence just doesn't make it true. So make sure that you're always thinking about whether the assumption is reasonable before using that multiplication rule. If you think that the outcome of event A is somehow going to impact the outcome of event B, then don't use this multiplication. If you think it's reasonable to think that they're independent, then you're good to use this formula here. Let's go ahead and look at an example. So example 1 says, suppose there's a 35% chance that on your drive to school, we're just looking Monday through Friday, a particular stoplight is green, 4% chance that it's yellow, 61% chance that it is red. We're going to answer a couple questions here. So part A says, what is the probability that you get a red light on Monday and on Tuesday? So the wording of this one is hopefully leading you to think that we do need to have an and problem here. Now they're saying that we need to get a red light on these 2 days. So what I'm going to do here is I'm finding the probability of a red light on Monday and another red light on Tuesday. So I know, because I'm thinking that Monday's event is independent of Tuesday, just because I get a red light on Monday doesn't impact my chances of getting another red on Tuesday. So I'm going to take the probability of red for Monday and multiply it by the probability of red on Tuesday. There's a 61% chance that the light is red, so I'm going to do 0.61 here, and I'm multiplying it by another 0.61. That gives me 0.3721. I know a lot of times students ask me, they're like, wait, Mrs. Soto, why is this getting lower? Why is there a lower chance when there is a really good chance that I get a red light on Monday? Well, by using this and here, you are narrowing the requirements. You're saying that there needs to be a red light on Monday and on Tuesday. That's a very specific event. 2 things need to be happening, so it makes sense that the chances of that happening would be a little bit lower. Part B says, what is the probability that you don't encounter a red light until Wednesday? Now, the wording here is a little bit trickier. They're not really telling you what's happening on Monday and Tuesday, but you know you don't encounter a red light until Wednesday. So that means on Monday, you would not have a red light. So I'm going to put not red. I don't know if it's green, I don't know if it's yellow, all I know is it's not red. That's Monday. Then on Tuesday, I again want not a red light. And you don't encounter a red light until Wednesday, so that means on Wednesday, it's a red light. If it helps, you could think about this as Monday, Tuesday, and then Wednesday. Now, I don't have this listed out exactly, but I can use my work from earlier. I know that the probability of not red is just 1 minus the 0.61, so that should give me 0.39. So there's 0.39 for Monday, 0.39 for Tuesday. Wednesday is when I hit the red light, which is 0.61. So 0.0928. With probabilities, you do want to make sure you're always rounding to 4 numbers after that decimal, because if you were to change this into a percentage, it would be 9.28%, which is still keeping things quite accurate, versus if you just wrote 0.09, then you only have 9% here, which isn't awesome. Again, this is decreasing, it's getting lower, because again, you are narrowing the requirements. You're telling me it's not red Monday, it's not red Tuesday, and then it's red on Wednesday. That's very, very specific. Part C says, what is the probability that you have to stop at least once during the week? Now, these at least problems, I think, are the hardest ones, so if you've been kind of half paying attention up to this point, make sure you're tuning in here. Now, if we're stopping at least once during the week, that means I encounter at least 1 red light. It could be 1 red light, it could be 2 red lights, it could be 3 red lights, it could be 4, it could be 5 for Monday through Friday. Now, before we actually solve this problem, what I want us to do is actually write out what this sample space would look like. Okay, now there's a chance that I don't have to stop at all. So I'm just going to put 0 stops. It would be a really lucky week. I get green lights the entire time. It's possible that I have to stop once. Maybe I have to stop 2 times, 3 times, 4 times, or 5 times. 5 would be my maximum if I'm going Monday through Friday. That's only 5 days. Now what we're looking for at least 1 stop, which means I really want to find this idea of 1 through 5. That's the event that I am looking for. Now I could find the probability of 1 stop, add it to the probability of 2 stops, add it to the probability of 3 stops, but that's going to get really crazy. So instead, I want us to use this idea that the sample space has to add up to 1. Now the only thing that is not in my circle and not in the event that I'm looking for is this 0 stops. So what we're going to do is take 1, that's the entire sample space, and we're going to subtract the probability that there are 0 stops. Okay, now if I'm not stopping at all, that means on Monday, it's not red. On Tuesday, it's not red. On Wednesday, it's not red. There's no red lights at all. So what we want to do here is think about this day by day. Every single day, it's not red. There's a 39% chance that it's not red. And I need that not red to happen every single time throughout the 5 days. So I'm just going to put an exponent there of 5. Okay, I'm going to go ahead and type this in. 1 minus 0.39 to the 5th. And I get 0.99097. That 7's running the 9. So 1, 0. So there is a very, very, very high chance, 99% chance, that I need to stop at least once throughout the week. With these at least once problems, you're always going to, I recommend always writing out your sample space or somewhat thinking about your sample space, and then subtract the thing that you are not looking for. Usually it's just the 0, so you'll take the probability of this thing not happening. So stopping was red, this is not stopping right here. Your exponent will always be the number of times that that's occurring. So in this case, there were 5 days, so this occurred 5 times. Okay, example 2 says you are taking a biology quiz tomorrow, but you decide that you'll just guess on all of the questions. You're just going to take a guess on each of them. You're not even going to read them, you're just going to guess. There are 5 multiple choice questions, each with 5 possible answers. What's the probability that you get all of them right, you get at least 1 right, you get your first incorrect on the 3rd question, and so on. Now, I'm going to get this problem started for you, and then I'll have you try the rest on your own. What I think is a little bit tricky about this one is they didn't straight up tell you the percentages. So you're going to have to do a little bit of work to get that on your own. So it's telling us there's 5 multiple choice questions. So that's kind of like the 5 days of the week that we saw in the last one. There's 5 questions. Each has 5 possible answers. So with these questions, I'm either going to get the questions right, I'm going to use an R there for right, or I'm going to get the questions wrong. I'm going to use W for wrong. Now, in order to get the question right, I need to pick the right answer. There's only 1 right answer, and it's out of 5. So it would be a 1 out of 5 chance, which is 0.2 or 20%. The probability that it's wrong, there's 4 wrong answers out of the 5, which is 0.8. So an 80% chance that I guess wrong, 20% chance that I guess right. Now that we have those probabilities identified, why don't you go ahead and try A through D. Once you're done, go ahead and play your video again, and you can check your work with mine. For part A, you were finding the chances that you get all of the questions right. You could have written this as probability of right times probability of right times 5 times, Or using exponents, you could have just used the probability of right to the 5th power, which is 0.2 to the 5th. Your calculator does give you that e, which we've seen several times at this point. It's e to the negative 4, which tells you to move that decimal 4 spaces to the left. So we get 0.00032, so very, very small chance that you get all of the questions correct. Part B was one of those at least one questions. I wrote out my little sample space where I have 0 right, 1 right, up the way up to all 5 of them right. I'm looking for at least 1, so that's 1 and above. Again, the only thing not in there is the 0, so I found the probability by doing 1 minus the probability of getting 0 of them right. If I get 0 of them right, it means that I'm getting every single one wrong, so that's 0.8, and that needs to go to the 5th power for every single question. 1 minus that gives me 0.6723, so there's a 67% chance that I get at least one question right. Part C said you wanted to get your first incorrect answer on the 3rd question. That means that the first 2 had to be correct or right, so we do 0.2 for the first question, 0.2 for the second, and 0.8 for the third. Part D, you want to get all the questions right except for the last one, so we're getting 4 right and then 1 wrong. Again, you could write it out like this, or you could use exponents, so you're getting right to the 4th power. So 0.2 to the 4th times 0.8, very, very small chance there again.